Welcome everyone to our latest webinar, Measuring the Thermal Conductivity of Cured Epoxy Samples, presented by Thermtest. I'm Angela and I'm your moderator for today's session. Today we will explore thermal conductivity in cured epoxy samples, a vital aspect of material analysis impacting numerous industries. We'll be focusing on the measurement platform Versatile, the MPV, and its critical component, the Modified Transient Plane Source Sensor, MTPS, both renowned for their accuracy and versatility. It is my pleasure to introduce our expert speaker for today, Kelsey Wood, our own laboratory lead. Kelsey's comprehensive knowledge and experience makes her a leading authority in the field of thermal conductivity measurements. We'll have a Q&A segment at the end, so feel free to drop your questions into the chat box at any time, and Kelsey will provide the answer for you at the end during the Q&A portion. Now, without further ado, let's get this started. Kelsey, over to you.
Thanks for the introduction, Angela. So as she mentioned, today we're going to be talking about the measurement of different types of epoxy using the measurement platform Versatile and the transient plane source method. So just a quick introduction on to our MPV. This is our mid-range measurement platform for testing solids, liquids, pastes, and powders using the combination of the transient plane source method, the transient hot wire method, and the transient line source method. So with this instrument, we're able to test for thermal conductivity, thermal diffusivity, volumetric heat capacity, and effusivity in the most straightforward and user-friendly ways possible. So with the MPV, there are a variety of sensors available that are suited for different methods and different sample types, starting with the Modified Transient Plane Source MTPS sensor. This is our absolute single-sided sensor for testing solids, paste, and powders, and automatically comes with the modules to test for 1D, anisotropic slab, and just standard bulk samples. We also just have the standard TPS module for testing solids, pastes, and powders. This is in accordance with ISO 2207-2. We have the THW sensor used to test liquids in accordance with ASTM D7896, and this comes in either room temperature or high temperature versions. And then finally, we have our TLS sensors to test soils, polymers, and soft rocks in accordance with ASTM D5334-22A, as well as the European IEEE standard. So getting right into it, what is epoxy? Epoxy is a term that can refer to a synthetic polymer, a resin, or an adhesive. Electrically insulating and thermally conductive epoxies are typically desirable for industrial applications as they can improve the reliability of high-performance electronic devices, especially through heat dissipation. Epoxies also offer many other desirable thermal and mechanical properties such as low shrinkage during curing, as well as high chemical and corrosion resistance. So in today's application, we're going to be comparing the measurements of filled versus unfilled epoxies. Unfilled epoxies typically have a lower thermal conductivity and are excellent thermal insulators. Our Loctite unfilled epoxy is a two-part adhesive that forms very strong bonds and is able to maintain its strength over a range of temperatures. So this is what we're going to be measuring today for the unfilled epoxy. Epoxies can also be filled with different compounds that can alter their properties and change their possible applications. So these fillings can be ceramics, metallics, carbon fiber, or other. So these can be added to increase the strength of the epoxy or to make it more conductive. For the filled epoxy today, we chose to measure the Prima Solder silver filled epoxy, and this would be expected to be much more conductive than the unfilled epoxy due to the addition of the silver particles. So both of these epoxies were two-part room temperature curing epoxies. Curing epoxy resin is a process of transforming the liquid into a solid by triggering a chemical reaction. So these two samples were each cured for 24 hours in identical round molds for symmetrical transient plane source testing with the MPV. So to test the samples of epoxy with the MPV, we use the standard transient plane source method. In a typical transient plane source experiment, two identical samples with flat surfaces are placed on either side of a TPS sensor. This can also be done in the asymmetric configuration if you only have one piece of sample available using the asymmetric modifier. So with this modifier, an insulative backing material is used to replace the other piece of sample that's missing, and this is accounted for in the analysis of the results. So the TPS sensor is made up of a double spiral nickel wire encased in a thin layer of polyamide insulation. So once the current is applied to the sensor, the change in the resistance of the sensor is measured over a specific period of time during the measurement. When running a transient plane source experiment, there are some important guidelines to keep in mind. So the first one is that the probing depth should be less than the nearest distance between the sensor edge and the sample boundaries, as this minimizes boundary effects. So this is where it's important to select the appropriate size sensor for your specific sample size. The average temperature rise is also an important factor to consider. So the temperature rise for the duration of the measurement should be between around 0.25 and 4 Kelvin. And this is just to maximize the sensitivity of the measurement on the sample's thermal properties. It's also important that the ratio of total time over characteristic time, which is what we refer to as TCT, is within the appropriate bounds, which would be 0.3 and 1.5. So to assist with the selection of these parameters, with these key factors in mind, the MPV software was designed with many features to facilitate the measurement process. With the automated sensor selection feature, the MPV automatically recommends the appropriate sensor to use based on the dimensions of the sample. So the dimensions of our epoxy samples were approximately 8 millimeters thick with 8 millimeters radius. So the software recommended the 2117 sensor with a 3.2 millimeter radius, and this accommodates for that smaller sample size and satisfies the TCT as well as the probing depth. We also have the proprietary intelligent transient plane source feature that's embedded into the MPV software. So this serves as a tool to assist with a selection of appropriate parameters to achieve the appropriate temperature rise, TCT, and probing depth for your sample. So the ITPS is fully automated. It runs a single sensing transient while reading information back to the software to ultimately determine the ideal test time and power to use for your sample. So when we use this ITPS function with our epoxy samples, we found the optimal parameters of 5 seconds and 100 milliwatts for the unfilled Loctite epoxy, and 2 seconds and 200 milliwatts for the pre-solder silver-filled epoxy. So then we use those parameters and ran some measurements on the sample using the MPV. And looking at our results for the measurements, we found that the Loctite unfilled epoxy had a thermal conductivity of 0.2 watts per meter Kelvin, a thermal diffusivity of 0.117 millimeters squared per second, and a volumetric heat capacity of 1.7 megajoules per meters cubed Kelvin. While the pre-solder silver-filled epoxy had a thermal conductivity of 1.9 watts per meter Kelvin, a thermal diffusivity of 1.849 millimeters squared per second, and a volumetric heat capacity of around 1 megajoule per meters cubed Kelvin. So these results were what we were expecting to find from these samples, as the unfilled epoxy was expected to have a much lower thermal conductivity than the pre-solder silver-filled epoxy. So that pretty much summarizes the measurements of filled versus unfilled epoxy using the MPV with symmetric transient plane source method. This epoxy could also be measured with other methods and other instruments, so please reach out to us if you have any questions, and I'll hand it back to Angela.
Hi, everyone. We are going to enter our Q&A portion. So I'll leave this up for a minute or two. So if anybody has any questions, please put them into the chat and Kelsey will happily answer them for you. But if you don't have any questions right now and you think of one later on, feel free to send us an email and we will happily provide the answer or point you in the direction of someone that can. Okay? That's okay. We don't have any questions today. That's quite all right. It happens. It's a lot to process, I know. But I want to thank you so much for attending our webinar on measuring the thermal conductivity of cured epoxy samples with Kelsey Wood. Thank you, Kelsey, for taking time out of your busy schedule to provide an educational opportunity to understand how the MPV works and how we can apply it with epoxy samples. Keep an eye on your inbox. We'll be sending out the webinar recording within the next couple of days. And as I said before, if you have any further questions, please send us an email at marketing@thermtest.com, and a member of our team will gladly assist. I hope everyone has a great day, and that concludes today's webinar. Keep an eye out. We have another one coming up in 2 weeks that you might want to register for. Have a great day, everyone.